Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. We continue chapter 8 DSC with melting temperature. Okay, so if we keep heating the polymer past its crystallization temperature, which is TC, we will reach another thermal transition called melting temperature or TM, whereby polymer crystal begin to melt and the chains come out of their ordered arrangement and begin to move around freely. So when polymer crystal it melt, they must absorb heat. And melting temperature is first order transition, and this means that when you reach the melting temperature, the polymer temperature won't rise until all the crystal have melted. So as we can see in this curve, the area below the curve is the delta H, known as the delta H. So melting temperature is known as the endothermic reaction because it absorbs heat. And you can look at the arrow. The arrow is going upwards, means that it is endothermic. So if your graph, if I give you the value and you want to plot the graph, it is either exothermic or endothermic. And then you need to if you choose the endothermic curve, so you need to make Tm going upward. Okay, if you choose the exothermic reaction, you will need the Tm will going downward. Okay, the dip will going downward, but the value is inside the area under the curve, the value of the delta H, I mean. Right, now we proceed with the next slide. This one is the DSC thermogram. As we can see here, the first peak will appear on the graph is the glass transition, which is TG. And as we can see here, the TG is at the center of the decline. Okay, this one is the exothermic reaction, which is heat is released. So TG will go in decline, TC will go upward, and TM will going downward. And the next graph is the cross-linking graph or the cure graph. And the last one is the oxidation, whereby the polymer or the material has been oxidized at certain temperature, which is at the high temperature, around 600 something. So a completely amorphous polymer, it won't show any crystallization or melting temperature. But the polymer with both amorphous and crystalline domain will show all the features above, which is TG, TC, TM. And if you look at the DSC plot here, we can see a big difference between the TG with TC and TM. So TG, no peak, no dip either, because there is no latent heat given off or absorbed by the polymer during the transition process. So both melting and crystallization involve absorbing, giving off heat. And the only things we do see at TG is the change in heat capacity of the polymer, because there is change in CP, but no latent heat involved with TG. Then we call it as the second order transition. What is latent heat? Okay, latent heat is actually the energy released or absorbed by a body or a thermodynamic system during a constant temperature process. An example is a state of matter change, meaning a phase transition such as ice melting or water boiling. Now we look at the other example, which is polyethylene triflate. This is the example of semi-crystalline polymer, which is linear polyethylene triflate, PET, okay, or isotactic polypropylene. Okay, we show this curve because it is the semi-crystalline polymer. We show all the peak. Okay, we can see that the curve which is the TG right here, is going inclined. Okay, so it is as endothermic. Okay, endothermic. So make sure um you see that this one dia tulis exo down, tapi dekat sini graph dia adalah menaikkan, TG dia naik. And then the first curve here is TC, which is going deep below. Okay, and this one is TM, which is going upward, deep upward. And please make a correction here. Okay, I want you to familiarize. If the TG is going inclined, so it's supposed to be endo upward. Okay, not exo down. Exo down happen if your TG going downward. Okay, and TC is upward, and TM going downward again. So please make a correction here, not exo down, it is endo up, endo up. Instrumentation, there are two types of DSC. We have heat flux DSC and power compensated DSC. For heat flux DSC, it is the same furnace heat, both the sample and reference. So the derived delta H, we must calculate the delta H, and it used the platinum resistant thermometer. For power compensated DSC, we have two separate heating for sample and the element, and we need to measure and just we can examine, or we can get the value of delta H directly from the graph, and it used the thermocouple. Okay, this one is the power compensated DSC. We have sample and reference. This one is heat flux DSC. For sample preparation, the material you need to have with you is um, the sample pan. Okay, sample pan uses for non-volatile sample. Types is aluminum, gold, platinum. Temperature is around negative 170 to 600. For film, we need a scissors, paper, sponge, and razor blades. And for hard sample, we need a razor blades and also the saw or diamond saw. Okay, this one is the sample crucible, which is the crucible that you need to place your sample inside it. And this one is the cover. And sample crucible match, we have a sample use condition for DSC, DTA, TGA, sample material, crucible material, crucible volume, use condition, and at different types of condition, atmosphere, temperature range, and depends on the types of crucible you want to choose. Okay, and we have different types of crucible. We have aluminium, gold, platinum, steel, copper, glass, sapphire, and alumina. The requirement for the material should be inert, and to the sample in the temperature range used, and should not exhibit any physical transition in the temperature range used, and the melting point should be sufficiently high. Basically, the sample size is between 5 to 10 milligram. If you want to use the large sample, it is up to 30 milligram. So the more sample, we can have a better detection limit, which is the larger peak, and we need to reduce the resolution. For the small sample, which is up to 0.5 milligram, the smaller peak, and we need to use a better resolution. And for example, separation of event occurring at similar temperature can be detected. Let's review the DSC curve. Okay, as I explained before, and as I show in the diagram that I draw on the pane. Actually, it is the same graph. The difference between these is the curve as a function of time is on the left and temperature on the right. So this one is referring to the endothermic process, whereby the TG is going upward and crystallization peak is going deep downward and melting temperature is going upward. This one is for temperature and this one is curve as a function of time. Actually, it is the same graph as we can see here. The first peak appeared is the melting temperature and the last one is the crystallization temperature if we plot it against time. And if you plot against temperature, um, the peak, the first scan hitting the melting peak will appear first, and when we cool it and the cooling temperature is, the graph will appear after the second heating. Okay, second heating, and it is in the cooling step, and the crystallization peak will appear below this. And we just plot the graph according to the previous I draw. TG, if the graph is endothermic, so the peak is going upward for TG and followed by TC and TM. Okay, it is more easier for you to understand. Now we look at the application of DSC. So we can measure the glass transition temperature, of course, and you can read it what is TG. Okay, so TG is the temperature at which the polymer change from a glassy rigid to the flexible rubbery state, or vice versa. It will influence the plastic end use performance. For example, if the TG you get is too high for the temperature under which the end product will use, the product will strong but brittle. Okay, let's say if you got your polypropylene sample, the PP is 265. Okay, so let's say you get 265 TG, but you want the TG which is below that, okay, below that value. So if you use your material which is high TG, but the requirement or your boss want the TG which is lower than 260, what will happen? So your performance, the performance of your product will be strong but brittle because the TG is not meet the requirement. If TG too low for the temperature under which the end product will use, the product will be too soft and easily deformed under load. For example, let's say the TG for PP is 265, right? So if you got the value for your PP sample, test by TG is below 265, so your sample will tend to be too soft and will easily deform when you put it under load. Okay, there are some several factors that influence the performance of your material, especially the TG. Okay, first is the additive. Okay, if you add a plasticizer or additive, it will affect the performance of the TG. Besides, you can also look at the chain length of your material, the also the molecular weight of your material. Okay, if your molecular weight increase, TG will decrease and crystallization will increase. Okay, the second application of DST, we can estimate the melting temperature. Okay, why we need to estimate the melting temperature? It is useful for determination of optimum processing condition, whereby above the melting point it will be too fluid and resulting rich on the molded part and some decomposition. And when below melting point, the molding will not fill the mold completely. It will cause crack and stress point in the part. And we can also determine the melting peak, which is the onset of melt peak, and also know the area under the peak, which is the delta H.